Justin Miller, Armstrong Call Physics here. We're gonna do some work. Do some work indeed. And work should make you think about something, right? Yeah, the physics work, right? Not going to work, not doing some chores. Work done by a force. What force could we possibly be looking after that may be doing work in this particular course? That's right. Electric field force, of course. All right, so this is what we want to start looking at, the work done by the electric field force. Work done by the electric field force acting on a charge. So we're going to make some assumptions here. Number one, let's just go ahead and assume that the only force being exerted on the charge in question is the electric field force, the force due to the electric field interaction with that charge, and thus substantiates the net force, right? So, what can we do with this? Well, if we have some charged particle, say it's a positive charged particle, Q, and we stick it in an electric field, we'll just go ahead and say we've got a uniform electric field, just for argument's sake. Just draw some electric field lines. T hat equals uniform. What's going to happen to this charge when we let go of it? And well, if the only thing acting on it is the electric field force, then what? Well, then there's going to be some net force. So we're going to go ahead and say let the only force acting be the electric field force here. So there's our electric field, there's our charged particle Q. What about the force? So what direction is the force? Number one. What do? Well, we go ahead and look at the force on a charge Q is equal to that charge Q multiplied by the electric field at the location of that charge Q. So that's a nice little expression there that gives us a correlation between the electric field force and the electric field acting on that charge Q under consideration. So if the charge is a positive charge, that force is in the same direction of the electric field. Charge is a negative charge, there's a minus sign in between these two vectors, and that just means opposite. So we go ahead and say, well, the electric field force, well, let me not call this F sub Q, it's a little deceiving. It's better to call F sub E. Force due to the electric field, not the force on the charge, force due to the electric field on the charge Q. So we have this. F sub E hat will be that way. And well, if we know the charge and we know the electric field strength, we know what the force is. That's a great. Well, but let's go ahead and not talk about just the force. We've already done that. Sure, there'd be some acceleration and changes in motion. But let's go ahead and think about, let's do red, this charge undergoing some displacement. So what if this charge moves from its initial position where it is to some final position? Whether the electric field force moves it, well, we're saying the electric field force is the only thing acting, so it has to be responsible ultimately for its change in motion. What can we go ahead and say with this? We can say that the electric field force is doing work, right? Work done by the electric field force moving the charge will be W equals, now this is a uniform constant field, so it doesn't have variance spatially, and we're taking just a point charge here, so the work done is just going to be equal to force vector dotted into the displacement vector, right? There we go. There's the work done by the electric field force. Fantastic. What does that resolve out into? Well, this resolves out into an F sub E delta X times the cosine of theta F sub E, where theta F sub E is the angle between the electric field force and the displacement that this particle is undergone, which in this particular case is 0 degrees. Electric field force is that way, the displacement is that way, that's fine. But this is just in general, right? How we treat dot products and ultimately work done by a constant force. So what can we get out of this? Well, we get that there's work done. Yeah, there's work done. The greater the distance is, the more work that's done by the electric field force. Well, again, if we're saying that the only force acting on it is the electric field force, then we've also got something that we can do. Since F sub E is equal to sigma F, what do we have? Well, we've got then that W F sub E is equal to the net work done on the charged particle. That is it. So, go. What does the net work done do? Well, the net work done produces the object's change in kinetic energy. Sigma W delta KE. Net work done produces an object's change in kinetic energy. Work energy theorem, that's a from last semester. So that's great. What do we got? We got some nice correlation here. So what can we do with this? Well, there's all sorts of little things that we can start to reconfigure. We could ultimately say that this quantity right here is equivalent to the net work done, which is then equal to the change in kinetic energy. We could expand things out. There's all sorts of little intricacies that we could pump into this, but the main point is that the electric field force is the only thing doing work. It instantiates the network, and then it is responsible for the charge's change in kinetic energy on which it acts. The charge under consideration. That is fantastic. All right, so just one thing to note. Just so you recall delta KE, what is that? 1/2 mv final squared minus 1/2 mv initial squared. M is the mass, that would be the mass of the charge under consideration. V is the final speed, V final is the final speed, V sub I is the initial speed, and there we go, there's change in kinetic energy. All right, so what we want to do is sort of investigate this a little bit and see if there's some other notions that we can kind of extract out of this, because we took a very particular case. Uniform electric field, yeah, we'll stick with that for a large part, but we took a positive charge moving in the direction of the electric field. But it doesn't necessarily have to be moving in the direction of the electric field. The electric field force will be in the direction of the electric field, but we could have taken some positively charged particle and threw it into this electric field in the opposite direction, right? So the positive charge could be moving that way initially. What happens? The force is in the opposite direction. It'd be slowing down as time goes on, right? Or we could release it from rest, or it could already be moving when it enters the electric field, moving in the same direction that it's going, in which time it undergoes an acceleration in the direction of its motion, speeding up, increasing its kinetic energy. Or it could be a negative charge. What happens then? So there's, again, all sorts of little things to consider here, and that's what we want to be able to do, is kind of decipher this all and quantify things like, hey, how fast is it going after it moves a certain distance? And yeah, you may say, well, we just use constant acceleration and that'd be fine. And that is true, but that's only true if the electric field is uniform, constant in magnitude and direction everywhere. What if the electric field is not uniform? What then? Well, you've got to rely on some other methods, right? You've got to be able to ultimately rely on work done, because the work done just depends on the force and the displacement. All right, so where do we go with this? Let us go and look at a couple little scenarios here, and yeah, kind of go from there. So let me finish up one little thing with this, just to connect some dots for this particular situation here. we could say that, again, this object doesn't matter if it's moving that way or that way. Oh, we're already saying it's moving that way, excuse me, it does matter. We're saying it's moving in the direction of the electric field. So in our particular case, we have here that the net work done is equal to the work done by the electric field force, which is F delta X cosine theta sub E. And we've got ourselves then F sub E delta X times the cosine of 0 degrees. Because again, the force is that way, the displacement's that way, so this is our specific case here. That's great, so cosine of 0 is just equal to 1. And we've also got that the magnitude of F sub E is equal to absolute value of the charge multiplied by the magnitude of the electric field. So, a little bit careful with that, because this is just magnitude here. Magnitude of the electric field, magnitude of the electric field force, absolute value of the charge, because again, the charge can be plus or minus. We're only dealing with magnitudes right here. So again, there we've got something with this, and then we can write this then, this F sub E, as sigma W is equal to Q times E times delta X. All right, so we're already saying that this charge is moving in the same direction of the electric field, because we said cosine of theta is equal to 0, being that it's a positive charge, and that's all good. So if we know what the charge is, it's positive, that's a positive value. We know what the electric field and the displacement are, those are both positive values too, because they're just magnitudes. We get that the net work done is a positive quantity, and thus there would be an increase in kinetic energy, because again, we'd have the Q E delta X is equal to delta KD. All right, so that's great. We can kind of correlate it there. If we know the initial velocity, we can find out the final velocity, or vice versa. All sorts of little things that we can do with this. But what happens if we just go ahead and say, you know what if this charge was a negative charge? Okay. Now consider Q being negative charge. Well, what would be the difference here? Well, let's investigate this a little bit. So we go ahead, stick in our electric field. We'll say that again. It's a uniform electric field. We'll go ahead and throw our little charge in here. This time it's a minus charge. There's our Q. And the first thing that I want to say is, or ask, what direction is the electric field force? And hopefully you say it is in the opposite direction of the electric field. Because again, we go back down to, or up to, it's up above me, up to this expression. The electric field force is equal to the charge multiplied by the electric field at the location. So, being that we have a negative Q here, we have to have that the force is in opposite direction. So we would have this by the very notion of things. There's the direction of the electric field force, is in the opposite direction of the electric field. All right, well that's fantastic. What do we do with this though, right? What can we do? Well, we've got to be a little bit careful. Because, again, charge can be positive or negative, and there's a consequence for that. So, let's say this to begin with. Let's say that this negative charge is like released from rest. What's going to happen to it? We release it from rest. If we release it from rest, which way is it going to go? Well, we release it from rest. That's the direction of the force. It will accelerate in the direction of the force. So this particular particle will go this way. And we just consider some delta x hat, some displacement that it undergoes. What do we have here? Well, we have that the displacement is in the same direction of the electric field. And, excuse me, in the same direction of the electric field force, but in the opposite direction of the electric field, which means that we got to be a little bit careful once again. So if we went ahead and started calculating the work done by this, well, let's go ahead and do this. The work done on this charge, work done by the electric field force on this charge is going to be equal to electric field force dotted into the displacement vector, which again will just be equal to F sub E delta x times the cosine of theta sub F sub E. And what do we get out of that? Well, what's theta F sub E going to be? That is the angle in between the displacement and the electric field force, excuse me, the electric field force, which is 0 degrees. Theta F sub E is equal to 0 degrees still. Cosine of 0 just gives us 1, and we've got then that the work done by the electric field is equal to F sub E delta x. Well, that's basically what we had over here, right? Cosine of theta is equal to 0. We just get F sub E delta x. Fantastic, but now is where we put in something else. Because again, we still have from this that the magnitude of F sub E is equal to the absolute value of Q multiplied by the magnitude of the electric field at the location of Q. There is the electric field force. So what happens if we go ahead and make that substitution in there? Well, we've got the work done by the electric field is equal to the absolute value of the charge multiplied by E times delta x. Well, again, if this is the only force acting on it, it constitutes then the net work done. So we have the net work done produces the change in kinetic energy is equal to the absolute value of Q times E times delta x. And that is exactly the same, right? Same thing that we got here, which is really a matter of, well, something that has to be the case. If we release this positive charge from rest, it would accelerate in the direction of the electric field, increasing its speed, increasing its kinetic energy. If we release this negative charge from rest, it's going to move in the opposite direction of the electric field, accelerating in that direction, increasing its speed, increasing its kinetic energy. This has to be positive. That has to be positive. That's why we need the absolute value of Q there, is because in those cases, well, releasing it from rest, it has to increase its kinetic energy. So, is there some way that we could sort of correlate this without having to take the absolute value of Q? And the answer is yeah, there actually is. We just have to be a little bit careful with how we go about it and kind of put things together here. Because again, we could have that this charge is moved in many different directions. It doesn't necessarily have to be the electric field force being the only thing acting on it. We could still just go ahead and compute what the work done by the electric field force is. And that should be able to be positive or negative, depending on, again, what direction the charge is moving. So what do? Well, let's do this. Let us consider this positive charge again, but consider it initially moving in the opposite direction of the electric field force. Initially moving moving opposite to the electric field force here. So I'm just going to draw in again the electric field like this. We'll just again assume it's uniform. There's our E hat. We'll go ahead and take ourselves a plus Q here. There's our plus Q. And now this charge is moving in the opposite direction of the electric field force. We've already substantiated that for a positive charge, the electric field force has to be in the direction of the electric field. Thus, if it's moving in the opposite direction, it would be moving that way. You may say, well, how's it going to move that way? I'd say, well, maybe we threw it in here. Maybe it just has some initial velocity that way. It doesn't matter. We can have it moving that way. Fantastic. So what do we have in this particular case in terms of the work done by the electric field force? Number one, should it be positive or negative? And hopefully you say the work done by the electric field force should definitely be negative because the displacement is in the opposite direction of the force being considered here. So we have the work done by F sub E is equal to F sub E dot delta X, which is magnitude of force times the magnitude of the displacement times the cosine of the angle between the displacement and the force under consideration. And in this case, again, we've got our delta X hat is that way, and we've got our F sub E hat is that way. That is 180 degrees. And the cosine of 180 degrees is equal to a -1. Oh, there's a negative sign in there already. All right, so what do we do with this? Well, we can go ahead and stick that negative sign in there and write this as negative F sub E delta X. F sub E is just some number. It's not a vector anymore, just the magnitude. Same with delta X, just the distance. And we definitely get a negative value here. And still we can go ahead and start saying, well, we've got that F sub E is equal to Q times E. Kind of dropping the vector signs with the magnitudes. Those are just magnitudes there. There we go. So what do we get? The work done by the electric field force in this particular case with the charge moving in the opposite direction of the electric field and the charge being positive is going to be equal to negative absolute value of Q, E, is delta X. All right, so we get a negative sign out there. Well, that makes sense because it's moving in the opposite direction, right? So that's a grade. Well, can we do the same thing with the negative charge and get the same sort of result? And hopefully you say, yeah, definitely, because everything's going to play out sort of the same. So we'll say, now a minus Q. There's our E hat. Here is our minus Q. The electric field force would be opposite direction. And if it's moving in the opposite direction of the electric field force, it's moving then in the same direction as the electric field. So we could have that this object particle undergoes some displacement in the same direction of the electric field. Fantastic. And color, color, color. We're using the blues there. What do we get now? Well, the work done by the electric field force is going to be equal to, again, the electric field force dotted into delta X hat, which is going to be equal to the magnitude of the electric field force, delta X times the cosine of theta F sub E, which, again, theta is equal to 180 degrees, displacement's that way, the electric field force is that way, which gives us a negative sign, cosine of 180 is -1, and we get W sub F sub E is then equal to negative F sub E delta X. F sub E we can write as absolute value of Q times E, so we get negative absolute value of Q times E times delta X. There's the work done. Same results, right? Same results. So with this, we can deal with positive or negative. What we want to do is make things a little bit easier on us, and that's kind of where we're at because we want to start to think about work done and how it is connected to some other types of quantities. And the big question is the electric field force a conservative force? That's a good question, right? So that's something that we want to start looking at, and that we will be looking at here in a few. So be right back, and we'll begin with that. Okay, so let us answer that question. Is the electric field force a conservative force when it acts on a charge? So we're going to look at a particular case here, and we can translate it in some other notions, but we're going to again consider uniform electric field and a charge plus Q to begin with. So we can take this electric field like this, and we can take said charge, go ahead and stick it here. Give ourselves a positive charge. There's a Q, and again, depending on which way it moves, it could be losing kinetic energy or gaining kinetic energy when it's only under the action of the electric field force. Or equivalently, if it moves that way, we could say that the electric field force is doing negative work, and if it works that way, moves that way, the electric field force is doing positive work. Because I've already substantiated that, again, for a positive charge, the electric field force is in the same direction as the electric field, right? So let's just write this out. The charge moves that way, then W sub F sub E must be equal to a negative value, right? And if it moves this way, we have the W F sub E, the work done by the electric field force, would have to be positive. All right. So again, that just traces back to the direction of the force and the direction of the displacement, negative work versus positive work. So here's a question for you. If, say, we do something like this, I take this charge and I move it from here to there, and just consider the work done by the electric field force, what amount of work is done? Or really, is positive work done or negative work done? And me moving the charge from point A to point B. So we'll say that we have some point A here, and we move it over here to point B. Well, we already said, if it moves in the opposite direction of the electric field, since it's a positive charge, there'll be negative work done by the electric field force. All right, so we did negative work. Uh-oh, what does that mean? Well, think about this. If I take this pin and I take it from this elevation right here, and then I lift it up, I move it up above it some distance, has positive or negative work been done? And the answer to that is, well, it depends what you're considering, right? I exerted a force, I moved it up. So yeah, I did positive work. But there's something else that's doing work too, the gravitational field force, right? If we're just considering that, well, the gravitational field force is downward. And if I displace this object upward, I'm moving in the opposite direction of the gravitational field force, and thus the gravitational field force, F sub G, is doing negative work. And we've looked at the gravitational field force, right? It's a conservative force. I can get the energy back by just letting gravity act on it. Release it, and it increases its energy. So the amount of negative work that was done by the gravitational field force in lifting this up is the same amount of positive work done in bringing this object back down. and the gravitational field force bringing the object back down. Well, let's think about this. I take this charged particle and I move it from here to there in the opposite direction of the electric field force. What happens if I release it from right here? From rest, what happens to it? It starts going off that way, right? Because the electric field force is still acting on it. So what do we have here? Well, we'd have that energy is kind of stored. That me moving it back here gives it more space to undergo a further acceleration and increase its kinetic energy. So me moving it back here stores more energy in the system because, well, again, now it can move from here to here and then keep on moving from there and continue to accelerate in the direction of the electric field force. So the point with this is the electric field force in specific cases is a conservative force. What are those specific cases? Well, the real specific case is that it's a non-time varying field, that it's static in time. It can be varying spatially and have all sorts of different functionalities at different locations in space, descriptively, but as long as it's not time varying, we have that it is a conservative force, or the force that it exerts on a charged particle is a conservative force. So you can imagine that there's some like wall here, right? If I release this particle from rest from point A, it reaches the wall with some final velocity based upon how far it went, the acceleration that it undergoes over that time and such things, right? Some final velocity. Well, if I move this particle back here, then release it from rest, is it going to be moving faster, slower, the same rate by the time it reaches this wall again? So, well, it's going to be moving faster, right? Because now it has this additional space to undergo that acceleration, increasing its speed. There we go. That's the essence of being conservative. That the energy that we put in moving it backward is just stored in the system and can be recaptured, regained. So, answer to this is yes, as long as E hat is not time varying. Which is something we're not concerned about right now. So it's a static electric field. Can be different at different locations, different directions, different magnitudes, but it remains that throughout time. We'd have the same thing if we had a negative charge, right? So if we can do it with positive, we can do it with negative. And just really quickly, if we had ourselves a negative charge here, we'd have that the electric field force is in the opposite direction of the electric field. There's our epsilon E hat, and this will be our E hat. If we move the charge moves that way, positive work's done by the electric field force, because the electric field force would be in the same direction. If it moves this way, negative work's done by the electric field force. If I take this charged particle and say it's at point A, and then I move it over to point B, what happens? Well, there's negative work done by the electric field force because we've moved it in the opposite direction. But if we release it then from point B, it moves back towards point A and continues to accelerate beyond that as well. Thus, again, we get the same sort of correlation here. So the only thing that we've really got to be careful with is it a positive charge or negative charge, and what direction is the electric field, right? That's kind of what dictates things. So all said, positive charges want to move in the direction of the electric field. If they're moving in the direction of the electric field is doing positive work. And negative charges want to move in the opposite direction of the electric field. If it's moving in the opposite direction of the electric field is doing positive work. There we go. So that's great. We've got an essence of a conservative force. What do we want to do with conservative forces? Well, before we dealt with the gravitational force and spring force, right? An elastic type of force. So that those two forces are conservative forces, thus they can store energy. And we define potential energy, right? The amount of stored energy, or changes in potential energy, really. So can we do the same thing with the electric field force? And the answer is definitely. The work done by the electric field force can be translated into changes in potential energy. If it's negative work, it's a positive change in kinetic energy, positive change in potential energy. The electric field force is positive work, it is a negative change in potential energy, a loss. So if we move this charge this way, negative work is done by the electric field force, but positive or an increase in its potential energy, increase in its stored energy. The more we move it this way in the electric field, the greater the amount of energy that's stored. Because again, when we let go of it, it's got all that space to go ahead and accelerate and increase its kinetic energy. All right, so let's do this. We've got the work done by a conservative force in general is equal to the negative of the change in potential energy regarding displacements within that conservative field or conservative force. This is how we extract out change of potential energy. So let's see if we can take this work done by the electric field force and write it out not in terms of the actual force, but in terms of the electric field, because that's going to be beneficial to us. So let's see. We said that before we could write this as F hat dot delta X hat. And we could change that delta X with a delta R. Doesn't really matter. Actually, let me just make it delta R so it's an arbitrary displacement vector. So we got a force vector and we've got a displacement vector. This would be considering the force of the electric field to be constant in its magnitude and direction for that matter, thus no integration required, and this would be a special case. Anyways, what do we get out of this? Well, we can write this F sub E as Q times E hat, then dotted into delta R hat. Now this time we weren't working just with magnitudes, we're working with vectors still here. This is in general. We got the same results for both positive and negative by using this. Can we get the same results by using this now? So what do we have with this? Work done is Q times the dot product between E hat and delta R hat. Well, that's going to be E delta R times the cosine of theta sub E. So we've got ourselves Q times E times delta R times the cosine of theta sub E. All right. So again, this is just the work done. We'll get to the change in potential energy. We want to make sure that this makes sense for what we've got going on. So let's go back to this positive charge. Positive charge, if we move it in the opposite direction of the electric field, we'll be doing negative work, right? Negative work done, we move it in the opposite direction of the electric field. Is that going to be the case here? Well, let's go ahead and see. For plus Q, where delta R hat is opposite E hat, we have that theta sub E is equal to 180 degrees, right? Okay. E hat's that way, delta R hat is opposite, or at least a component of it is, and we've got that going on. So what do we get out of this? The work done by the electric field, or the electric field force, say really either at this point, is going to be equal to Q E delta R times the cosine of 180 degrees. That's equal to -1, so this would be equal to negative Q E delta R. We've got negative. Q's positive, E and delta R are just magnitude. So it comes out to be the right sign. Negative, check. If instead we move it in the same direction, well, this would turn out to be positive because that would be 0 degrees. This would turn out to be positive. That checks out. So that's for a positive charge. What about a negative charge? Q is equal to a minus charge, and delta R hat is in the same direction as E hat. We've got this. We've got the work done by the electric field will be equal to, well, we're still saying that it's Q E delta R times the cosine of theta sub E, and we have what? We have this delta R is opposite E hat, so theta sub E is equal to 180 degrees. That's great. So this is going to be equal to -1 here. So we've got negative Q E delta R, which you may say, oh shoot, that turned out to be -2. Shouldn't it? Same direction, I'm sorry, I'm messing this up. 0 degrees. Same direction as E hat. Theta sub E is 0 degrees, cosine of 0 is just equal to 1, so we're left with this, Q E delta R, which you may look at and say, oh, that's positive, but Q is equal to negative here. So the work done by the electric field is going to be equal to negative, which checks out. If we move a negative charge in the same direction as the electric field, that will make it in the opposite direction of the electric field force, which means that there's negative work done. And likewise, we could go ahead and say, well, what if it moves in the opposite direction? Moves in the opposite direction, theta sub E is 180 degrees, we'll have a negative sign from this and a negative sign from Q that cancel each other out, and we'll get positive work done. So the big picture is that this expression right here can deal with both positive and negative charges, and really any displacement correlation with respect to the direction of the electric field. So this is good, written in terms wholly of the electric field and the displacement. The force is embedded in there. So now what we can do is take this and say, well, the work done by the electric field force is a conservative force, and what can we get? Well, we've got ourselves that delta PE can be written as, well, negative W sub E, which then gives us the change in potential energy of a charge moving through a uniform / constant electric field, because again, this is assuming that E is constant here, is equal to negative Q E delta R times the cosine of theta sub E. Where that theta sub E is the, again, the angle between the electric field direction and the displacement's direction. And there we go. Here it is. That is a grand right there. Grand indeed. Changes in potential energy. So this is what we wanted to start to look at here, was exactly that. So with this, again, we can start calculating all sorts of things. This is change in potential energy a charge that is displaced in a uniform T-hat field. You say, well, what if it's not a uniform electric field? Then what? Well, that's a good question. That's a good question. I'm glad you asked that. What if E hat is not uniform? Well, what does that mean if it's not uniform? That means that it varies spatially. It can vary both in its magnitude and in its direction. So what do we have then? Well, the work done by a force that is varying over displacements is integral from some R initial to some R final of F hat dot dr hat. The definition of work done by a varying force, right? Over some displacement, we'd have to integrate the force over the displacement. So we'd have to have the force written out in terms of its variation with respect to position. All right. If E hat varies, F hat varies. Same way. We still have that F hat is equal to Q E hat at any given location in space. That's always going to be the correlation. Force varies, well, it's varying because the electric field varies. So what do we have then? Well, we have the work done by the electric field on moving a charged particle within a electric field that's varying is equal to the integral from R initial to R final of Q E hat dot dr hat. There we go. What can we say about the change in potential energy? Well, delta PE would be equal to the opposite of this. Is equal to negative the integral from R initial to R final of Q E hat dot dr hat. That's about the best that we can do without knowing the functionality of E itself. And again, Q here can be positive or negative. It depends really, right? It depends on which way the electric field is with respect to the direction of the displacement, or the direction of the change in position of the charged particle Q, whether we have an increase or decrease in potential energy. It all kind of follows out the same. All right, so this is more generalized. That's a special case where we've got a constant electric field, magnitude and direction. Both of them come in handy. But again, a little bit more general there. We'll take a look at some consequences of that as time goes on. All right, so I think we'll leave it at that for now. We'll come back and start to open up another barrel of monkeys, can of worms, or whatever you want to call it. Good things, good things. I'll just say that. Some more good things. All right, take care. Until next, be well.